All right. Good morning, everyone. Welcome back. We will continue to introduce binary search trees in chapter 25. Last time we looked at the implementation of the binary search tree, and we studied the algorithm, how to insert and delete elements from a binary search tree. And we also look at the visualization of a binary search tree. At the end of the class, we look at the iterator. In the binary search tree, you can traverse all the elements using an iterator. Now, the iterator is defined in the iterable interface. The iterable interface is a subtype of the collection interface. It's a supertype of the collection interface. So the collection interface is a subtype of the iterable interface. Let me show the diagram so you're going to see it. I'm going to go to the this is the diagram for the binary search tree UML diagram. So I'm going to go to the this diagram. I think I'm gonna go, maybe I look at the wrong book. I'm gonna launch this book. Okay, this is the book. Okay, so this is the diagram right here. Now, look at this diagram here. We have this is the tree interface. It's a subtype of the collection, and collection is a subtype of the iterable interface. All right. So this is the BST. It's a subtype of tree. All right. So this, I'm going to have another tab here. So let's open another tab. So now I'm going to go to the iterator right here. All right, so this is iterator right here. The iterator. So where is this in the overall architecture in the Java API? I'm going to open another tab, so I'm going to show you this here. Okay, now this is another tab I'm going to show you here. It's in this diagram. So here's the diagram. It's in the right here, the collection framework diagram here. All right, so we're going to look at this diagram. You can see this is the collection interface, and here is iterable. Iterable, it's right here. And so from here, the iterable, you can get the iterator. So the iterator, this is the iterator right here. So this is where we have, this is the iterator right here. This is the iterator. All right. if we have this iterator and we have it, we implemented the BST, we must have this iterator. So we can write a code. So this write a code, you can use the for each loop to traverse all the elements. So this is what we did. So here is, and using for each loop, so here is a string in the BST. So every string in the tree, and we're going to get the string, traverse it, and display it in uppercase. So this is here. Now it is the order, the traverse order. We use the in order. So this is the natural in order. So this is the, here's a blue, as the Danube and green, jade and maple and purple and teal. So this is the alphabetic order. All right, so now we're gonna look at the implementation. So the implementation, it's right here in this, here, the implementation. So we're gonna implement it, and this is the binary search tree here. So this is to implements the tree interface. All right, so you're gonna write your code and just practice and fill in the code, and then you can compare it. You can open another tab and you can compare. And so while you type in here, and you can see and compare it with the answer. So you can get the answer and right here, and by clicking this answer button to get the answer of this. All right, so I'm gonna just click on this answer now. We'll get everything here. I'm gonna show you. So here, this is the BST class. So here we have all the constructors, and so I'm going to go down. Look at here's search method, insert method, and this is here the we have in order and post order and pre order, and now this is the get the root here. This is get the path. All right, this is delete method. So delete method right here. All right, so now we're gonna come to this iterator. We're gonna overwrite. Oh, very sticky, huh? Doesn't hold this. Just have to do this. Okay. All right, just go. You see this right, iterator right here? Okay, this is the iterator. Oh, gee, this is so. All right, here is the iterator. Iterator. All right, this is the iterator right here. The iterator method, and we override it. It's defined in the iterable interface, so now we have to override it in the concrete class. So override it, and it's going to return an object of this iterator. So this will return new, and here, what's the iterator we're going to have? We're going to define our own iterator. It's in order iterator. All right, so this is an in order iterator. And we have now, this is in order iterator implements java.util.iterator. So internally, we're going to keep all these elements in an array list. And here's in order. We're going to perform this in order to traverse all these elements in the tree and put it into the array list. So this is what we do. This is the array list. Here's a list.add all these elements. So now you see how we write recursive code here. Has next. So now we have, initially we have the current points to the beginning of the array list. So we have all the elements now. This constructor here, in order iterator, will get all these elements into the array list. And we have this, the current points to the first one. So now current move to the next one. So that's index is 1, then index 2, index 3. So that's goes. All right. So here is has next. The current is still less than the list size. Okay. So that's return true has next. All right, so how do you get the next? So list.get current. All right, and then after this, then current is incremented plus. So this, you can see this is. All right, so that's how we're going to implement it. So you see those methods here. So I'm going to go back to this one here, and this is we have the iterator, so we use the iterator. So this, it's very nice data structure. It's actually very useful. It's a classic data structure, binary search tree. It's not in the Java API, and we design and implement it, and we make it fit into the Java API. So we use here, it's a subtype of collection, and so it's iterable, and it's a very nice data structure. You can customize it. So you can go back here and say, hey, I can use a different order. Instead of using this in order, I can use it and make it post order, make it a pre-order, and other orders. It's your choice. Okay. All right. Any questions? And you see the beauty of this data structure. Question? Okay. I think, can you turn on the camera, please? So, thank you. Now, and this is the last part of this class. We design our own data structures, implement it. So you get a sense, what's a data structure? Data structure is objects, so a data structure is an object that contains other objects. So it's a container object. And this is going to contain a lot of data. And you need to organize the data to manipulate data, to add, remove, and search. And how do you do this efficiently? Okay. So we have a variety of data structures, and they've used it for different purposes. Okay. So now you have this custom data structure. It's a binary search tree. You're going to compare it with the other data structures we have. So we have the list data structure. The list data structure, you have the notion of the index, but in the binary search tree, there's no notion of index. You cannot just say, I want to get a 10th element in this binary search tree. No, there's no notion of index. All right, in the list, when you do a search, in the worst time situation, it's order of n time. It's actually, it is, the search is going to be order of n time on average for the list too. But for the binary search tree, on average time, the tree is actually very well balanced. So that's the time, it's the height of the tree, it's order of a log n. And log n time is very, very quick time for all these three operations: search, insertion, and deletion. And when you do a list, so, and overall, and the average case, when you do a search anywhere and search and insert anywhere and delete anywhere, it's all order of n time. So the order of n time versus order of log n time. This is a very good data structure if you have application and you need to just do this three operations, but you're going to give up something. There's no notion of index. And so the list has a strict sequence, has the index. All right, I'm going to give you another very similar application. We're going to use the data structure in this application. It's using a binary tree, but it's not the binary search tree this time. So this time, the next application I'm going to look at it is this data compression. Okay. Data compression, it's very common task. So you use zip files, and zip file is compression of a file. You compress the file and into a zip file, so the size is reduced a lot. Okay. So there's an algorithm to do this. So there are many ways, many different algorithms now in the commercial application. There's one very early on, but it's still used in telecommunications. This is called a Hoffman algorithm for data compression. So I'm going to introduce this, and we're going to see how we're going to implement it. All right, so this algorithm was invented by Hoffman. He was a PhD student in the 50s at MIT. So, and his dissertation is on the data compression, and he invented this data compression approach. So the idea is this. So when you have all the data, it's all the text data. So you have all the alphabets, right? And you have the code. So when you do data communication, you send all this data out, and you have to assign the code. It's a binary, becoming binary. So like A is assigned a binary code, and B is assigned to another binary code. So this is the code is sent out the binary digital information, and for this data communication. So you want to have, if you have a text, you want to have minimize the number of bits, number of bits, 0 and 1s, number of bits when you do send out the data out. So that will save money. And yeah, the way we Hoffman coding is this. It has a Hoffman coding tree. So it builds a coding tree like this. So suppose we have a text, a very simple text like Mississippi. All right. So here is a Hoffman coding tree. So for every text, so you do an analyze, and then you have to build a tree. It's called a Hoffman tree. Given a text, okay, you're going to build a tree. And give another text, you're going to build a different tree. So it's every tree is different. The text has different Hoffman tree. So for this text, the Mississippi, and this is the tree here. So the tree is like this, and you can see this is the tree. And we have this is in Mississippi. These are the characters, MPSI. So here, the idea is that frequently used characters in a text. So in this text in Mississippi, there's a lot of I's, a lot of S. So you're going to see a lot of I, a lot of S. And so this frequently used characters, we're going to assign the short code. You're going to save the time by doing this. So that's the key idea here. So that's what you're going to get is, you get this tree here, and so I, the code is 1, and S, the code is 0, 1, and P, the code is 0, 0, 1, and M, the code is 0, 0, 0. So that's the code, the character, the code, and here, and we have just a reference, a frequency here. It's as a reference, the frequency. So I appears 4 times, S appears 4 times, and P appears 2 times, M appears 1 time. So the ones frequently used, and we have the short code for it. So that's the key idea for this. All right, so now you have this tree. you have the text. So you send the text to the receiver, and at the same time, the tree is also sent to the receiver, and the receiver will translate this compressed text and using the tree. So the compressed text using the tree here, you can look at this. I have the text here. It's encoded. So Mississippi is encoded into this. This one right here is encoded into this. Okay. All right. And now I'm going to have to decode it, receiving it. So this is all binary. And now how do you to receive to decode it? So decode it, you have to have this tree. Now you get the tree. Look at the tree here. Is this 0, 0, 0? So you just go to 0, 0, 0. So that's M. And then after this is 1. 1 is I. So 1 is I. And then 0, 1 is S. So this is, you got the idea how this is going to be translated into the text. Okay. All right. Hey, now, how do you build the tree? So the question is here, how do you build this tree? That's what we're going to study here, is build this Huffman tree. Okay. All right. See all this, and it was invented in the 50s. It's still used now. It's something, and we can do it in the future. Is we're going to invent our own algorithms and for new applications. And so this is the we're going to learn it. Not only just learn this Huffman coding tree and learn the techniques we can use it for the future. All right. So the way we're going to build this Huffman tree is this. We're going to construct a Huffman coding tree. And here's the algorithm I'm going to use. Is we're going to begin with a forest of all the trees. Okay, it's a forest of trees. Each tree contains just a node for a character. And the weight of the node is the frequency of the character in the text. So you have a node, you have the character, like M, and then you have frequency, how many times it appears in the text. So that's right here. Look, this is a diagram here. We have, this is the character M, and the weight is 1, and the character S, the weight is 4, and character I, the weight is 4, and character P, the weight is 4. See this all here. All right, so we have all this. So we had to first do the analysis. You give me a text, okay? You may have a lot of characters, the contents. So I'm go through and this to analyze it and get this frequency. And then we're going to build this is the forest. So this is the forest, okay? Eventually we'll get a tree, just one tree. So now the forest, a lot of trees, right? So what do we do the next step? Next step, we're going to repeat the following actions. So here is the second here step. This is do a repeat. So how do you repeat it? This is the one. We're going to pick the smallest frequency. So this is one, and here's 2. All right. Combine this together into a tree. In this combined tree, you have the new frequency becoming 3. It's 1 plus 2 is 3. So this is the new one. All right. And keep doing this repeatedly. So this is 3 and with 4. So you can pick either this 4 with this 3 or this 4. So we're going to just pick this S. So now combine this 2 trees together, and with the new, using this is the new weight is 7. There's 3 plus 4. And finally, so you only have 2 trees, and you combine those 2 together, and the weight is 11. All right, this is the tree. Now we're going to begin to assign the code. And each node, you have 2 branches at most, right? So this is 0. The left is assigned 0, and the right is 1, and left is 0, right 1, and left is 0, right is 1. Oh, so that's the tree. We have the tree now. All right, this is just a real sample, small sample, Mississippi. In real application, and you may have a large text. So the tree is, well, anyway, you have just all this, look at all this characters in the ASCII code, and the maximum is 128 characters. So the number of nodes is 128. And that's but the frequency is going to be different. So you can look. All right. So that's the algorithm, and the algorithm here, and this is actually, it's called a greedy algorithm. It's greedy algorithm. Greedy algorithm, it is you just choose here is to choose the frequency, the smallest frequency always selected, and then combine together all these trees. All right, all this, now we're going to implement it. How do you write the code to implement it? To implement it, we're going to use this data structure is binary tree. So this is binary tree because this is a binary tree. So our data structure will be a binary tree. So this is very similar to our data structure of BST. So in BST, we have the binary tree, but this has order property. In this case, we don't have this order property, but there are something we're going to combine all those things we have learned so far is how do you pick the smallest frequency 2? So this is 1 and 2. How do you pick it right? How do you do it efficiently? So since here we have learned, we're going to use a heap. We use a heap to store all the trees in a forest until the heap becomes just 1 node. All right, so you can see that, and very elegant. And this is the implementation. All right, so I'm going to jump to this code, and so this is the Huffman code. All right, here we're going to prompt the user to enter a text. You can enter any text. So, and now we get the frequency of the text, all the characters. So this is the counts for all the characters. So this is get frequency. You can see this is get frequency here is right here. Just assume you have the ASCII code is the maximum, and get all these characters, all the possible characters in ASCII code is 256. So this is the, and get all the count for all this text. Okay, so that's frequency. All right, so now this is a get Huffman tree. It is a tree here. It's a tree here. It's a tree. All right. So this is a tree here. It's a tree. We're going to get that. And we're going to build a heap. So here we're going to have a heap for this. So we learned the heap. So here is okay. When we introduce sorting, so we have that heap. So here is the heap. So I'm gonna get the answer here and just do it quickly here. You're gonna see this is the heap. So okay. All right, so we have this heap now, and we're gonna put this initially. So this is the tree here. And initially we have and the each character and with the frequency This is the frequency for the character. So the frequency is count. Here's counts I, and this is the this one here. Yeah, here's the counts. Is the counts brackets I, and this is the character. Okay, in the tree. So we're gonna just add it into the tree. Here is this is the for loop. We're gonna add it all. All right. So because it's a heap, so what we're gonna do is we're gonna remove the smallest always first. So when we define this tree, how are you gonna compare the tree? So here's the criteria we're gonna compare the tree. So the trees, we're gonna make it comparable tree. So here the tree, look at the tree has, so there's two constructors, and one is this initially, so you just have this wet element. So there's another one, so you combine two trees together. Okay, so the initially here, this is for the tree node, and it's wet and element. So when you combine this together, so you create a new node, and you have left is this T1, and the right subtree is T2, and the wet is the combining of T1 and T2. So how you can compare it? So we compare it this. It's opposite. If this is this root is the weight is less than T's, okay, that root and that weight. So now it's just reverse the order, return positive. Normally, it's what we do is naturally we're gonna return negative, right? It's less is negative, equal is 0, and greater is positive. But this, because we're gonna purposely reserve the order, we're gonna reverse the order. Yeah, we need to reverse the order. All right, so look at this node. Node, you have the element, weight, and left, right, and there's a code. We're gonna assign it into it. All right, you can see that total, and this is a very elegant implementation using the data structures we have, using the trees and using the heap, and we implement it in this program and the Hoffman tree. You get a Hoffman tree, and here you do this is and get the code. So for each character in the tree, so this. And so here, for example, you enter text is Mississippi, so you get the character, what is the ASCII code for the character, the frequency, and the in Hoffman tree, and what's the code. So if you type something different, hello, all right, just for example, so you're gonna do compile and run, so you're gonna see a different thing here. So that's hello, and this is L is appears 2 times, and so the code is the shortest. Okay. Okay, so this it's a very interesting application, a compression. So you can see it and get some inspiration and for this data compression. And there are different algorithms for data compression. This is one. It's very early one. Yeah. And data compression. It's very interesting. So we pick up in this textbook as the example because it has a very good idea and also has elegant implementation and utilizing the data structures we already learned. Okay. I'm just going to get heads up what we're going to do next one. So this is the binary search tree. We're going to continue to introduce another binary search tree in the next chapter. It's called AVL tree. So it's a subtype of the binary search tree. Has additional property. So the additional property is it's guaranteed to be balanced. And this binary search tree is on average is balanced, but in the extreme situation, it is degraded into the linear structure. All right, So I guess I'm gonna stop here. We're gonna continue next time. And also I want you to have a chance to look at all the exercises in this chapter, the program projects in this chapter, and I'm going to give you some discussion and give you some hints next time in the class. But I want you to first read it. Yeah. All right, any questions? Okay, if you have questions, please stay and have a good day. Bye.
Have a good one.
Okay. Thank you. Bye. Stop recording.